Hi, Parth. So let's start today's class. And the first thing that I do every time is just I go over Sakai and the week tab and see what we have for the week. So in week 5, we're going to discuss the nonlinearities topic. And the nonlinearities topic is basically related to chapter 8. And it has basically 3 parts. So we have the interaction models, we have the log models, we have the polynomial models, and then a possible combination of the 3 models. What I cover in the class on Zoom, on our Zoom meeting, would be similar to what you see on chapter 8 of your textbook, but it will have also other examples or more in-depth analysis of some of the models. Okay, so make sure that you complement your reading of the chapter of your textbook with your notes from the class. What you have here also some videos that I have recorded previously for other classes related to nonlinear models. You have stata example on the log models. You have a stata example on interaction models. What you're missing is a stata example on the polynomial models, but I'll make sure that we have a video on that by the end of the week. Okay, and remember you have, this week you have quiz 2 and it's on my lab and it's on Friday for 24 hours. So before I start, I just want to make sure that we are on the same page. So last week, we didn't cover everything that I was supposed to cover due to we had the link issue at the beginning of the class, so we had like about 30 minutes missed from the class. Last week, we were able to cover heteroscedasticity, just an introduction to multicollinearity, and we still have to cover the remaining of multicollinearity and the omitted variable bias and other forms of misspecifications. So to overcome this problem, so I have posted for you some videos or 3 videos on multicollinearity, which I asked you to watch. And what I'm gonna do today is, before we start our 5th week topic, I'm going to cover the missing parts of last week, making sure that I finish multicollinearity and I finish omitted variable bias and other specification issues. It might take half of today's class, but this is an important topic that we cannot cancel, right? So I have to cover it. And then we will make up for, every time we have like a certain lag in topics, I'll make sure that we are covering this with additional videos. And on your part, you're supposed to watch whatever videos I post for you, and I send you a notification on that. And also take a note of any question that might arise while watching the video, and then you ask me when we meet during class time. Okay, so if you don't ask me any question about these videos, I'm gonna assume that you guys have watched it, you don't have any problem with it, and I'm going to briefly cover it, like briefly, and then add the remaining parts that I want. Of course, we will have a stata practice. So let me share with you my iPad. Okay. Again, if you have any questions, just stop me, because you guys used to send me in the chat room. Most of the time I don't see it, so just make sure any question, just open your mic and ask me as if we are in class. Okay, so what we've done is we covered already in the week, this is week 4 topic, okay? So let me write here, this is week 4 topic, which is about the violation of the OLS assumption. We were done with heteroscedasticity, what's the meaning of heteroscedasticity, how can we detect it, how can we overcome it by using the robust standard error. So we're done with this part, okay? We started multicollinearity last week, and I just gave you a brief introduction on multicollinearity. And today I'm going to start from here, and then I'm going to cover the misspecification errors. It shouldn't take much time. Okay, so in multicollinearity last week, I said that, okay, when I talk about multicollinearity, I can have two types, perfect or imperfect. Okay, so when you see me just saying multicollinearity, just all the time assume that I'm talking about imperfect, because I assume that we are not dealing with the perfect one. What is the perfect multicollinearity? The perfect multicollinearity can happen because of two things. Number one is the dummy variable trap. Okay, the dummy variable trap that I have explained last week. So you check the notes about the dummy variable trap. When I have a dummy for females and a dummy for males, and I assume that I only have two gender types, males and females, if I include both dummies with an intercept already included in the model, then this would create a perfect multicollinearity issue, and theta will drop one of the dummies for me. So you go back to last week video towards the end when I was discussing the dummy variable trap. The other thing is I can do a mistake by repeating a variable twice. So I have a model in which I have income. It depends on age and age. So I'm kind of doing a mistake of repeating a variable twice, and age with age is 100% correlation. So I'm creating a perfect multicollinearity in the model. So I'm assuming that I'm not dealing with dummy variable trap. I'm not repeating a variable twice. And if I do this assumption, then anytime I mention multicollinearity, just remember I implicitly mean it's the imperfect one. So let's talk about the imperfect one. What is the imperfect multicollinearity? So imperfect multicollinearity is I have a model yi, so this is yi, is equal to beta naught plus beta 1 x 1i plus beta 2 x 2i plus ui. Imperfect multicollinearity or multicollinearity in general is only about the x's. So I have x1 and I have x2, and the correlation between x1 and 2, R1, 2 is simply a notation for the correlation between x1 and x2. So sometimes I write it R1, 2, which is correlation between x1 and x2, or I write it as CORR x1, x2. If this correlation is not equal to 1, or -1, let's say 1 in absolute terms, then this is called imperfect. So imperfect multicollinearity, okay? So we are dealing with some number, which could be 0.8, could be -0.7, or it could be 0.1, 10% correlation, 80% correlation, a negative correlation of 70%. All of these are different numbers that you can get for an imperfect multicollinearity. And this is what we see in real life. So when I say in real life, let me give you an example that I like, which is about the physical performance. So if I'm saying the physical performance of a certain person is equal to a certain intercept, alpha naught plus alpha 1, the height of the person, plus alpha 2, the weight of the person, plus certain error term. So I have I here because I'm assuming that I have a sample of, let's say, 10, 30 people, whatever. So as you can see, this type of model, this is a good example of imperfect multicollinearity, because everyone knows that we do have a correlation between the height of the person and the weight of the person. The higher the person, it could mean that the higher the weight. Okay, so there is actually this equation which we know, which is known as the ideal body weight calculation, which says that weight is equal to a certain equation with the height of the person, right, plus VI. And this means that, okay, I do have some connection here, and this is about the ideal body weight. Okay, so that means that, okay, that everyone knows that there is this connection between the two. So if I have a model like this, and I'm taking this model to theta to estimate height and weight, they do not have 100% correlation, but they do have a high correlation. So if I include both variables in the model, I would create some type of imperfect multicollinearity. So this imperfect multicollinearity would be reflected in the R square of this model. So the R square of this model, you can call this R square as R square of the weight function. It's not the R square of the main model of the physical performance, it's the R square of the weight function. This R square will not be equal to 0. It will be equal to a certain number because of the imperfect multicollinearity. So this coefficient will not be accurately estimated because I do have, I'm sorry, I should say this coefficient. This coefficient will not be accurately estimated. And the same goes with this coefficient because of the connection between the height and weight. And at this point, I want to remind you of the 3 videos that you have multicollinearity part 1, 2, and 3. In parts 1, 2, and 3, we are dealing with the coefficient being estimated and the standard error of the coefficient, how they are affected by the multicollinearity. So if I'm saying that physical performance, let me write it as a physical per pp, physical performance, which is alpha naught plus alpha 1, the height of the person, plus alpha 2, the weight of the person, plus VI, which is simply this model. I'm just writing it in terms of abbreviations, okay? So if I have this model, then if I do have a correlation between HW, correlation between height and weight is not equal to 0, then I do have imperfect multicollinearity problem in the model, okay? And what does that mean? Alpha 1 and alpha 2, the standard error of alpha 1 and the standard error of alpha 2, all these will not be accurately estimated. So they will not be accurate. The coefficient that reflects the impact of height on physical performance will not be accurately estimated. The same goes with the coefficient that reflects the impact of weight on physical performance will not be accurately estimated. Why? Because both are affected by the connection between height and weight on physical performance. So when you check the 3 videos here, I'm talking about one of the second and the third, I'm talking about how the alphas or how the coefficients will not be accurately estimated. And in the first one, I'm talking about how the standard errors are not going to be accurately estimated. So I want you to go over these. So, okay, let me go back. So when you think about it, okay, what is the t-statistic of the first variable, which is height? Height. It's going to be equal to alpha of the height, right, hat, minus alpha of the height under the null over the standard error of the height of the person. And the same, you can repeat the same for the weight, okay? So for the weight, alpha hat weight minus alpha weight under the null over the standard error of alpha hat weight, okay? So if this is not accurately estimated because of multicollinearity, and the same goes with this one, and if this one is not accurately estimated and the same goes with this one, then I'm going to get misleading results on the t-statistic. So the t-statistic would be inaccurately estimated. So I'm going to get misleading results about the t-statistic. So the t-statistic is inaccurate because it depends actually on the coefficient and the standard error. And also, if you remember, this one is used to compute the confidence interval, then inaccurate. If you remember that the t-statistic is actually used to compute the p-value, then inaccurate. Okay, if you again remember that this one is used to compute the r square, then inaccurate. Same goes with this is used to compute the f stat of the model, again inaccurate. So everything is going to be misleading. You're taking a model that is problematic, and out of this model, you're estimating it and getting more and more problems, more and more misleading results. Okay, so when you watch the 3 videos, again, I'm referring to them because these are very important. Where are they? Okay, here. The 3 videos, parts 1, 2, and 3, I'm talking about how or the details on how these coefficients are not accurately estimated and how the standard errors are not accurately estimated, okay? So let me stress on the very important point, which is about the standard error. Let me just make sure. Okay, because I'm here. Okay. So the most important point that you will get out of these videos is about the impact of multicollinearity on the variance of the coefficient. So remember, or I want you to recall that the variance of the coefficient, whether you call it alpha or whether you call it beta, let's keep it beta because everyone we use it most of the time, beta j, is equal to the sum of the squared residuals over n minus k minus 1 over the variance of x. This is what you know, and this is xj, okay? This is what we know from OLS if I don't have any problem of multicollinearity. However, if I have multicollinearity or in the presence of multicollinearity, this variance will not be accurately estimated because this variance would have something called the variance inflation factor. So in the presence of multicollinearity, I'm just repeating it, over the variance of xj would have an additional term here, and this additional term is called the variance inflation factor. This part is called the variance inflation factor. And this is, I already mentioned that in the multicollinearity videos. We abbreviate it as VIF. And as the name suggests, it's a certain term or a certain fraction that inflates the variance. It's a certain component or a certain factor that inflates the variance. So it kind of magnifies the variance. Okay, so in the presence of multicollinearity, the variance of beta will not be the same as the variance of a regular OLS, which assumes that we don't have any multicollinearity problems. In the presence of multicollinearity, I have a certain problematic factor, which is called the variance inflation factor. And if you go back to the videos, and I'm assuming that you have watched these videos already, this R square J, it's the R square of the, we call it the auxiliary regression, which is the regression of X on the remaining X's in the model. So to make it clear, if I'm looking at the very first example, which is this one, I do have a model in which I have physical performance is regressed on height and weight. If I take weight and regress it on height, so x1 on x2 or x2 on x1, whatever. So I'm taking one of the x's and I regress it on the other x. This is called auxiliary regression. It's a regression of the x's. The R square of this auxiliary regression is the R square that we use it into the variance inflation factor. It's the R square used here. So that's why we call it R square J, because it's the R square coming from the regression of xj, let's say, on xm. Okay, if I have two x's, xj and xm, then it's the regression, it's the R square of the regression of xj on xm, and I take it here. Of course, if this R square is equal to 0, if this part is equal to 0, then it's gone. I don't have any problem, and I'm going back to the variance of OLS, which assumes I don't have any multicollinearity problems. Okay, but in real life, if I do have an R square that is not equal to 1, then this variance would be inflated by the amount of the R square. So let me give you an example. Okay, and just I want you to make sure that here I'm talking about the variance, right? But of course, if I take the square root of this, then I'm talking about the standard error of beta hat J, which is used in the t-stat and the other computations. So if you take just the square root of that, you will go back to, you will get this term, the standard error, okay? So I'm talking about the variance, assuming that you guys understand that its square root is the standard error. So let me give you an example. Suppose that the R square of x1 on x2 is equal to 0.5. What is the variance inflation factor? The VIF is equal to 1 over 1 minus R squared, right? 0.5. Then this one is equal to 2. So the variance of x1 will be inflated twice because of the 50% correlation between x1 and x2. So if I have information about the variance of, suppose that, I'm just making a number, okay? Suppose that the variance of beta hat 1, which is x1, is equal to 0.41. Then in the presence of multicollinearity, then this one would be the variance of beta hat 1 would be inflated by the VIF. So the 0.41 would be doubled because of the presence of a 50 or 50% correlation between x1 and x2. Then this would give me a variance of 0.81. What if the R square 1, 2 is actually bigger? It's 0.95. Instead of 50%, it's 95%. So you can say, you can actually imagine it like this. x1 is equal to alpha 1 plus alpha 2 x2 plus ui. Then I'm talking about the R square. So when I say R square 1, 2, it's the R square of this regression, x1 and x2. So if I'm saying it's 0.95, then the VIF, again, at this point is 1 over 1 minus 0.95, then I have a 20 times inflation. The variance of beta would be inflated 20 times. So the variance of beta 1 would be equal to 0.41 inflated 20 times, it's equal to 8.2. So I want you to imagine that every time the higher the correlation between x1 and x2, the higher the variance of x1. So the variance of x1 would keep inflating as the correlation between x1 and x2 increases. So there is also, as you check the video, there is also another measure instead of the VIF. Some people used something called the tolerance test. So what is the tolerance test? How much you can tolerate this regression? Tolerance test, it's actually the inverse of VIF. So you just get the VIF and it's the inverse of it. So having said that, these numbers, when can I tell that this is acceptable or this is not acceptable? This regression is, yes, has a multicollinearity issue, but I would accept it. It's not major issue, or I will not accept it and I have to deal with it. I have to do something to correct it. So we do have something like a benchmark. Our benchmark is, our benchmark is 10 for the VIF. So we're going to have to say if VIF is equal or exceeds 10, so 10 times inflation, the variance is inflated 10 times or more, then it's a problem. Okay, if the tolerance test is the inverse, then I say, or if the tolerance test is less or equal to 0.10, because it's the inverse of this one, so it's going to be 0.10, then again, it's a problem. Okay, so this is your benchmark. So every time we're doing a test using the VIF test as we have it on Stata, my benchmark is 10. If it's 10 or more, then I'm going to say it's problematic. I have to do something. If it is less, then I'm going to say, okay, if there is a multicollinearity issue, but it's a mild issue, I can accept it. Remember that I'm just saying I have a model in which I have yi is equal to, let's say, lambda naught plus lambda 1 x1i plus lambda 2 x2i plus lambda 3 x3i plus ui. For each x in the model, I have to test the VIF. So I would take this one and I have its own regression. x1i has alpha naught plus alpha 1 x2i plus alpha 2 x3i plus vi. And I'm going to have a regression for x2i. Let's call it beta naught plus beta 1 x1i plus beta 2 x3i plus another error term. And I'm going to have x3i, which is equal to delta naught plus delta 1 x1i plus delta 2 x2i plus mi, which is the error term of this regression. For each regression, I'm going to have an r square. So this is r square of x1. This is r square of x2. This is r square of x3. And each one is going to have its own VIF of 1, VIF, so I'm going to use the r square, VIF of 2, VIF of 3. And if I have a VIF, I can take the inverse of it and I can say, okay, I have tolerance test for equation 1, tolerance test for equation 2, tolerance test for equation 3. For each one, I have to double check what's the VIF, what's the amount of inflation. And we do have also an average of the 3. So average of VIF 1, VIF 2, VIF 3. And this is actually what we care about. If I do have a big model, then I'm not going to take each equation separately. I really care about the average inflation in the model. So in Stata, it's actually, our life is easy in Stata. Like the equation, if you do it manually, it's easy, right? Because it's just made out of the r square. However, in Stata, it's very easy command. So you first have your regress command, y, x1, x2, x3, and you just type VIF. And the VIF that you type right under the regress command would give you actually like this table where it has the VIF for x1, x2, x3, and it has like here an average, and this is what we check. Also, you might check the VIF of each one separately, making sure that it's less than 10. Okay, so if you have a question about, okay, what's the VIF of x2, you just read it from here. What's the VIF of the model, you read it from here. Okay, just make sure that each of these VIFs is less than 10. Okay, so what if it's not less than 10? So what we do? So if it is not less than 10, based on the VIF, actually VIF is just one way of detection. And I would say it's the formal way of detection. So VIF, tolerance test, it's a way of detection. You can also use the correlation. So you type correlation x1, x2, x3. This would give you the correlation table between x1, x2, x3, x1, x2, x3. Each variable with itself is correlation 1, 1, 1, right? And then you check this triangle and see what's the amount of correlation. This method, I use it for students who are just taking the first class or the first course in econometrics, which is called the Foundation of Econometrics or Econometrics 1, in which they don't deal with formal tests, right? They just look at the correlation, which is a very simple statistical tool that you can use in order to make sure I don't have a high correlation between variables. And in this introductory course in econometrics, I ask students to make sure that this correlation does not exceed 80%. But for our course, which is the second level of econometrics, which is more advanced econometrics, I would ask you to use the VIF or the tolerance test. I will also ask you to detect what you see with your eyes. So when you do the regress command, there are things that you can see that can give you hints that you might have a correlation issue. So if you see things like R square, it's very high. I do have a very high R square in the model, okay? And this R square is coupled with insignificant coefficients. So I do have high R square, insignificant coefficients. Why I'm saying insignificant? Because of the variance inflation factor would make the variance high. And if the variance is high, then the t-statistic might be low, getting closer in absolute terms with the zero, towards the zero, making you fail to reject the null or accept the null when you could have rejected it. And again, I'm assuming that you have watched the 3 videos on multicollinearity because I'm discussing this in details. Okay, so you can detect it by checking it with your eyes. Okay, R squared is high, insignificant coefficients, right? And or few significant coefficients, and this would give you a hint that there might be a multicollinearity problem. This is just with your eyes. You can use the correlation command, as I said, or formal test, VIF, and tolerance test. And with the VIF and tolerance test, it has a benchmark. 10, no more than, or 10 or more is a problem. 0.10 or less is a problem, okay? So this is about the detection. So how can you detect it? What are the possible sources of multicollinearity? Like why I'm getting multicollinearity? So the possible sources I'm assuming that you already know that I said before, perfect can arise from repeating a variable twice, or dummy variable trap. So just remember these two are here for the perfect. Dummy variable trap, variable repeated twice. Now I'm talking about the imperfect. Why I can have an imperfect multicollinearity. We have an like one of the sources, it could be like an overdetermined model. What is an overdetermined model? An overdetermined model is a model in which I do have many x's, look, the number of x's is greater than the number of equations or the sample size, or let me call it n. So number of x's we counted by k x's are greater than the sample size. I assume that we don't do that, right? I assume because all the time we're just talking about maximizing the sample size. So this one would be like you have a number of equations is less than the number of columns, okay? So you can say it's a small sample size. Don't do that, okay? Small sample size. So you can easily overcome an overdetermined model by maximizing your sample size. So I'm not saying that I have 5 x's or 5 information I want to gather about a certain person, age, education, gender, years of experience, and so on. So I have like 5 variables to gather about a certain person. However, I have only 2 people. So 5 points of information about only 2 people, it's an overdetermined model. Maximize the number of people, or maximize your sample size above 5 so that you're avoiding the problem of an overdetermined model. The second source of multicollinearity is the model specification. One of the important model specifications that can lead to multicollinearity is polynomial models. And I'm sure that you understand that if I do have a model that has beta n plus beta 1 x1i plus beta 2 x1i squared, this is a multicollinearity issue between x1 and itself squared, right? We will talk about that. So this one would lead to perfect multicollinearity because of the model specification, okay? Whether it's acceptable or not, then this is what we will discuss in our next topic. 3, which is the limited range of observations. So the data collection method, So you're basically, let's say I have a certain project, I'm doing a certain project about income, about income and consumption. And I'm collecting income range from 0 to 20K and 40K. And I'm trying to see how they are connected with consumption. If I stop here and my range is only from 0 to 20, I'm sure that I would get high correlation, because people who have an income of 20K or less per year, they do have very similar consumption behavior. However, if you expand your sample and allow for people who get 40 or even 80 or even 120K per year, then we would minimize the possibility of multicollinearity, because the wider the range that you will get on the X side or the regressor, right, the less and less possibility of correlation between regressors. Okay, so the data collection method, if you have a limited range, then definitely you have a problem, multicollinearity problem. So try to widen your range, right? Don't use a limited range of observations, okay? So that you try to avoid any possible multicollinearity. When I talk about the consequences of multicollinearity, I already mentioned that, right? So the beta hat is inaccurate based on, let me just here summarize it. So the main consequences of multicollinearity, we said that already in video 1, inaccurate beta, right? Large variance of the beta, let me call J, like to make it general. Number 3, low T statistic, high confidence interval, because the confidence interval is made out of the standard error. If the standard error is inflated, the confidence interval would be large or wide. So the confidence interval is wide. High R square, high F statistic. You would look at the model and say, wow, I do have a very nice R square. The model is jointly statistically significant, but how come I do have insignificant coefficients? So this is a sign, like from the consequences, you would be able to say that, okay, these are the hints of having multicollinearity, and let me check using the VIF. Okay. All right, so let me stop here. I would ask you guys, you have the data of the CPS 12 DTA data set. We were working on it last week. I want you to go ahead and do the VIF and tell me what is the VIF. Someone is gonna share with me the screen. So last week I had Parth was sharing his screen. So today maybe Dan or Othman can share the screen and show us what is the VIF. And as I said, all what you need to do is to type a regress command of the model that you have and just type under it VIF and tell us what is the VIF of the model. Othman, can you do that?
I wouldn't be able to share my screen. So the way I use my Stata when I called the help desk, it's not a downloadable. I'm using it through like multiple different links that take me to like a virtual version of like our online computers at school. Because when I was talking to the help desk, he said the only available version of Stata is for professors.
Oh, really?
Yeah. So he was like, as of last semester, it was available for students for free. But this semester, it's only available for professors. So
Okay.
like they were telling me I would have had to like pay all this money for it. So I was just using it through a virtual computer. So I wouldn't be able to share my screen while
Okay,
doing
can
it.
you actually do it now on your virtual and then let us know what is your values for the VIF?
Yeah, just bear with me because the
Sure.
way the virtual computer works, it's like it takes me to like a PC version
Uh-huh.
of my computer. It's really slow. So like
How
that's why
about,
it took me like the whole weekend to work on the homework.
okay, so how about Dan? Can you do it?
Using free version, so
Mhm.
it's kind of the same thing. I'm
Say
using
that again.
the virtual lab
Mm-hmm.
for SATA, so it's kind of the same thing.
You're saying it takes time?
Yeah, I'm using the free version, the one on the virtual lab,
Yeah.
so it's kind of slow.
Yeah.
I'm logged in right now,
Okay, let me continue
but
as, yeah, what I'm gonna do is that I'm going to continue as you guys open your virtual state, and then when you're ready, you can stop me. So all what you need to do is you need to get your CPS 12.dta, and then you just need to regress your model. So in this model, we have the average hourly earning as a function of beta naught plus beta 1 age plus beta 2 bachelor plus beta 3 female, right? And then what we need to do, and this is of course we have an error term, so we need to regress this model in theta. And after we regress this model in theta, we need to check multicollinearity. So these are the two things that both of you, Dan and Othman, you can start your virtual stata as I'm working on the lecture. And then once you get your stata working, it shouldn't take like more than a minute to type
yeah,
your data.
also, the virtual lab doesn't save your file. So every time I log in, I have to re-download the file from the class.
Yeah, you mean the DTA file?
Yeah,
But I
it
think
doesn't
it's,
save. It doesn't save on a virtual lab.
yeah, but I remember you can save it on somewhere in your computer. Let's say you work on a certain do file, and when you're done, you can save it to your own computer, right?
Yeah,
Yeah, but I
yeah.
have to work on the virtual lab. You know what I mean?
That's fine. That's fine.
The way the virtual app works is like you can't upload data from your computer to the app. It's only data downloaded on the app. Like I know what Dan is saying because when I was doing the homework, I was like, if my screen would just kind of like go black, I lost everything. And I
Wow.
would have to start from the beginning. Yeah. Because it's really weird. Like regardless if it's downloaded on your computer or not. Because
Mhm.
technically it's like as if you're using a computer lab from school.
Yeah, yeah, yeah. So it all depends on the network. Uh,
Yeah.
anyways, okay, guys. So you can, yeah, you can start logging into your virtual computer,
Okay.
and as I explained the lecture, and once you have it, as I did explain on this slide, it won't take time. So you just do the regress of your y on the set of the axes, and then you do the VIF command. So you check for multicollinearity using VIF. And once you're done, you just stop me, and then we can share the numbers, and I'm going to show it to you on my computer, making sure that we are all on the same page. Okay, guys?
Okay.
Mm-hmm. All right, so okay, so let's move on. So the last part of the topic of the previous week, which is let me just I found a nice example that I can share with you before I go on. So in this example, talking about multicollinearity. So in this nice example, we have consumption, which is the petroleum consumption in a certain state. Okay, so this is the petroleum consumption in state I. So we have a set of states, and we trying to figure out, okay, what's the connection between the petroleum consumption and the number of miles on a highway. So this is mile, and the gasoline tax. So this is tax plus the registration, which is the motor vehicle registration in the ith state. plus a certain error term. And remember, we're talking about states, so this equation is going to be repeated for each state. So assume I have the states go from 1 to 50. So I'm going to have 50 equations. So when you check this model, okay, so this is, as I said, this is the urban highways in miles. This is the tax on gasoline. This is the motor vehicle registration. When you look at this model and assume that you did your regress command in Stata, so you would get like CI hat is 389. This is an actual example that I got the numbers for you, so I felt like it's an interesting example. And mile minus 36.5 tax, minus 0.061 registration, and the R square or the adjusted R square of this model is equal to 0.919. The standard error of the coefficients is 10.3, 3.2, and this one is 0.043. When you check, okay, this is statistically significant, this is not. So why is that? This is, when you look at these variables, you need really to think, okay, what each variable reflects, okay? So when you look at mile and registration, this variable and this variable, there might be a correlation between the two. There's a possible actually correlation between the two. Both reflect the size of the state. So mile and registration, right? The higher the number of miles in a state, the more cars in the state, the higher the number of registration. So both reflect size of the state. So how can I move forward with this model? Why I do have this variable insignificant? I do have these two significant. And I do have a high R square. So this is what you can detect from vehicle registration, the higher the motor vehicle registration increases the consumption of petroleum in a certain state. So to move on with this model, you have really to think about what can you do? How can you overcome this problematic issue or multicollinearity issue? So you can actually drop the collinear variable. So you can drop registration because it's either or. I can either drop mile or I can drop registration. I can't have both in the model. And before you drop any variable, you have to be 100% sure that you will not run into another problem, because you might drop one variable and you run into another problem, which is called a misspecification error. So you misspecified your model because you have excluded important variables. So if this model, let's say, is about a macroeconomic theory, and then you drop an important variable that is supposed to be there in the theory, then you run into a misspecification error. However, in this model, it's not related or not directly related to a certain theory that it's telling us you have to keep mile and registration both in the model. So you're kind of flexible to drop one of them. So if you drop, let's say, mile from the model, and you do the regression again, you would get results as follows. And again, this is actually based on a certain, on actual data set. It's not like a made up numbers. 0.7 minus 5, 3.6 tax plus 0.186 registration. And then this is 0.012. This is 16.9. I don't know if you can see the 16. This is 5, 3, and this is 16.9. Now I do have significant coefficients. The adjusted R square is not as high as the previous one, right? And now, as you can see, the registration standard error is less. It was inflated here, right? It was definitely inflated. And the inflation is coming from the variance inflation factor, and the variance inflation factor is inflated because of the high R square between registration and mile. Okay? So this is just an example of a multicollinearity problem. Let's go ahead to the next and the last problem that we can get in our models, which is, you go back to the first slide, which is, okay, we're done with heteroscedasticity, multicollinearity, and we're left with the misspecification errors. The misspecification errors actually consist of 4 important problems. What we're going to stress on is simply one of them, not all of them, because the remaining 3 are going to be covered in the next topics. So misspecification error, I can have errors coming from omitting a certain important variable, or called omitted variable bias. Okay, I can have a problem arising from the wrong functional form. So let's say my model is supposed to be polynomial or quadratic or with a log or with the interaction term, and I decided to have it just linear. Number 3, errors in variables. So I might have some errors in computing my variables. My variables are supposed to be all in dollars, and I have one of them in cents. I don't have data set on a certain variable, and I took another variable as a proxy or as a reflection to this variable. So this could be also another issue, right? And number 4, simultaneous causality. So every time we're saying that y is a function of x, so x affects y all the time. Since the beginning of the semester, I was all the time talking about x as being the independent, y as being the dependent variable. Now, when I talk about simultaneous causality, how about that y can also affect x? So we will be talking about a possible econometric problem that can arise from the two-way causation. X affects Y, but also Y affects X. So I have to take this into my consideration. So in the misspecification errors, we are going to focus on the very first one. And let me actually say more general. So let me just say it's omitted variable problem, okay? So omitted variable a problem, and then for the bias, I'm going to have certain conditions to call it omitted variable bias, okay? So I'm going to focus on the omitted variable problem, and then we will go into just briefly talk about the 3 because they are actually related to coming topics. Okay. So what is omitted variable? So let me call it A, omitted variable problem. So omitting a variable is like, as the name suggests, you actually were supposed to have a certain variable in your model, but by mistake, you forgot this variable, or by mistake, you omitted this variable. So I want you to imagine that you can have a variable, a model like this. yi is equal to beta naught plus beta 1 x1i plus beta 2 x2i plus ui. Okay, now suppose that this one is called the correct form. So this is the correct form, but for some reason you forgot x2. Okay, so the wrong form is like this: alpha naught plus, I don't know why this node is just too big. Okay. Alpha naught plus alpha 1 x1i, okay, plus a certain error term for this model. And I'm going to say, okay, this is the wrong form because I forgot x2, or I omitted x2. So it's a wrong form of the model because of omitting x2 by mistake. I want you to imagine that if you omit x2 by mistake, it would be inside this error term. In other words, this VI would have the variable I forgot with its coefficient plus the error term of the correct form model, which includes the other factors, okay? So if this happens, then the impact of x1 on yi, which is supposed to be beta 1, will not be accurately estimated by alpha 1. So the impact will not be the same. In other words, we can write it this way: the expectation of alpha hat 1 will not be the same as the actual beta 1 or the actual effect. Why? It's because x2, which is related to x1, was omitted from the model. And if it is omitted in the model, like from the model, which is in model 2, then let me call this one the correct form as model 1, wrong form as model 2. Then I can say if x2 and x1 are actually related, I can write them into this form of the model. x2i, which was omitted, is actually related with a certain intercept and a certain partial slope with x1i and a certain error term, let's call it epsilon I. And I'm gonna call this 3, where 3 is actually the equation that relates the excluded variable. You can call it actually excluded or omitted variable with the included variable, okay? And I'm sure that you know that this slope or partial slope is made out of the covariance between the two x's, like what we did with y and x. So it's made out of the covariance of the two x's divided by the variance of x1. Or in other words, this lambda 1 is a function of the correlation. So this one is a function of the correlation between the included and omitted variable, right? It's made out of the combination of the covariance and the variance of the omitted and the included variable. So how about we can simplify or rewrite model 1, which is this one, by including equation 3. So let's take 3, which is x2, and substitute it right here and see our model. So if I do that, then I'm going to substitute 3 in 1. So we get the following. Our model is equal to beta naught plus beta 1 x1i plus beta 2. I used to have here x2. I'm going to substitute it with its contents. It's equal to, x2 is equal to lambda 2, lambda 1 epsilon. So I'm going to take it here. So I'm going to say beta 2 is equal to lambda naught plus lambda 1 x1i plus epsilon I plus ui. Now I'm going to multiply, right? Multiply this, remove this bracket, and then combine terms. So beta naught plus beta 1 x1i plus beta 2 lambda naught plus beta 2 lambda 1 x1i plus beta 2 epsilon I plus ui. Look at the terms. So this one is just made out of constants. I can combine it with a constant. So I'm going to say, okay, I'm going to combine all the constants together. So beta naught plus beta 2 lambda 0, and this is a certain constant, plus I'm going to take anything that has x1i together, right? So it's going to be like, okay, beta 1 plus beta 2 lambda 1 x1i. So this is my new slope. And I'm going to take anything that has error term together. So my new error term is going to be this one. So if I rewrite this into back to the alphas, so this one I can call it alpha node plus, I can call this one alpha 1 x1i plus, I can call this one as an error term vi. So yi, right, yi, right, which is this one, which is this model, made out of alpha node, alpha 1 x1i, and a vi. When you look at the content of alpha node, when you look at the contents of alpha 1, when you look at the contents of the error term, they are right here. When you open them up, this one is opened into this one is opened into this one is open into this. So there is no way that they are equal, okay? So when you write it, it's actually like this. Let me just take this on the same slide so that you're not lost. So I can write it like this. There is no way that the expectation of the intercept, which is alpha hat node, is equal to the expectation of beta hat node plus beta hat 2 lambda node. They are not equal. It's never equal to beta node, which is the original model. Okay. Same goes with the partial slope, which is alpha hat 1. The alpha hat 1, which is actually our main concern. It's always the case that, yes, I'm interested in the intercept, but I'm more interested in the partial slopes or the effect of x1 or x2 and so on. So I'm more interested actually in alpha 1. So alpha 1 is equal to this, right? So it's equal to beta 1 plus beta 2 lambda 1. And there is no way that this is equal to beta 1. What is beta 1 and what is beta node? These are the actual ones in the correct form of the model here. The correct form of the model had beta 1 and beta 2. So the wrong form, which is alpha node, can never be equal to beta node. Alpha 1 can never be equal to beta 1. So let me just take this up here. Okay, so the one that I want you really to focus on is, if you look at this component, it's equal to this component. But I have a certain additional part here that is making the problem. This one is made out of beta hat 2 and lambda hat 1. The beta hat 2 is actually coming from the equation or the main equation of the y. So it reflects how important the omitted variable which is in our case x2, to the dependent variable y, okay? And then what about this other part is this one reflects how important the omitted variable, which is again x2, to the included variable x1, okay? So if I don't have this part, then I don't have any problem, right? Because the expectation of beta 1 would be equal to beta 1. This is what I need. But actually, because forgetting a variable, which is x2, or omitting the variable, which is x2, I'm running into a problem, or I have a certain additional part that is making my coefficient not equal to the truth. And this part, we call it the bias, the amount of the bias. And the amount of the bias is made of two components: a part that reflects how the variable that I omit, or the variable that I forgot by mistake, for example, is important to the dependent variable, and how the variable that I forgot is important to the included variable, which is x1. So you can write it this way: the amount of the bias, or the amount of the gap. You can think of the bias as the gap between your estimation and the truth. Okay, so this is, I want you to think about it like this: a bias is the difference between my estimation and the truth. Okay, like my estimation and the truth. This gap, and this is an expectation, this gap is called the bias. All right, so based on what I just explained on the previous slide, I can summarize this amount of bias as, let me just remove this, because this is not what I wanted to say. Okay, but this is for your information. So the amount of the bias, which is the difference between the estimate and the truth, is coming from, or depends on, the beta hat of the omitted variable, which is x2 in our case, and a function of the correlation between the included and the omitted variable. Okay, so in our model, you can think of this one, beta omitted, as being beta hat 2. And in our model, this function of the correlation is actually lambda 1. This is in model 1. This is in model 3. Okay, so the amount of the bias is actually related to how important how important the omitted variable to the y, okay, and how important the omitted variable to the included variable. So I can write it this way in case you are lost. The bias is equal to the coefficient of omitted variable times the correlation between omitted and included variable. Okay, so these two parts are related to these two parts. Okay, of course, if the bias is 0, then I don't have any problem. Like, this is the best thing that can ever happen. Like, the amount of the gap between my estimation and the truth is 0, then that's perfect, right? So back here, so if I do have this part is 0, I don't have any problem. Then this one would be equal to this one, and I'm done. But this would be like a very ideal world. Okay, so if I do have the connection between the two is 0, then that's perfect. Okay, so let me give you an example. Suppose that, and I like this example, it's related to attending class. Okay, so this example related to the omitted variable bias. I call it bias if the two conditions are satisfied, these two conditions, this one and this one. It's important to the y, it's correlated with the x. If these two conditions happen, then I call it a bias. If they don't happen, like just one of them, then I call it just omitted the variable problem. It's just a name, okay? So, where is it? Yes, here. Suppose that I have a regression in which I have the final exam score of a group of students is equal to a certain intercept, plus it depends on whether students attend the class, whether this class is inside or online. Beta to study, if you study, plus UI, and I have a group of whatever, 10 students. So this I or this regression is going to be repeated 10 times if I have 10 students. Okay, suppose this is the correct forms. Okay, so this is correct form of the model. Now suppose that I did a mistake and I estimated the final exam score depending on just an intercept, beta hat 1 attending the class, and this is the wrong form. Okay, now as you can see, the difference between the correct form and the wrong form has one variable that I omit. So the omitted variable is study. So study is omitted from model 2. Now, in order to determine the bias, I have to decide on these two things, right? Where is it? Just here. Okay. One thing, I just want to make sure that okay. So I have to make sure that the study which I omit, how important it is to the dependent variable or the final exam. I'm sure that attending or studying, studying is the one that is omitted. Studying and the final are highly correlated. So in terms of this part, I'm sure that the variable that I omit, which is study, it's highly important to the final exam score. Next, how important is study to the included variable attendance? Is it true that students who attend the class are also the same students who study for the exam? Most likely, yes, they are highly correlated. Students who study are the same students who are concerned about their grades and attend the class. So we need to figure out how this is related to our example. Okay, so two things. We need to figure out the direction of the bias. So of course, beta hat 1 is not the same as beta 1. Beta hat 1 is not the same as beta 1. So the beta hat 1 is biased. Why? Because it includes the impact of the variable I forgot. So the question would be, what is the direction of the bias? Is it positive? Is it negative? So the direction of the bias would depend on the two things we mentioned. It depends on the correlation between study and the final exam. So the correlation between the omitted and Y. I'm sure it's positive, right? The more that you study, the higher your final exam score. And also it depends on the correlation between study and attending the class, which is the correlation between the omitted variable and the included variable. I'm sure it's positive. So positive times positive would give me a positive bias. So I can go back here and I say, yes, they are unequal, but I can be more specific and say that actually it's overestimated. It's overestimated because of the positive bias. It already includes the impact of the positive correlation between study and final, and the positive correlation between study and attempt. So that brings us to possible combinations that I can get. Okay, so the direction of the bias If it's positive times, sorry. If it's, I just want to make it less confusing. If it is positive times positive, then I'm going to get a positive bias. If it is positive times negative, I'm going to get a negative bias. If it's negative times positive, again, I'm going to get a negative bias. If it is negative times negative, I'm going to get a positive bias. Negative times negative is positive. If it's 0 times whatever, positive or negative, then I'm gonna get a 0 bias, which is the best case scenario. Or if it's anything, negative times 0, then I have a 0 bias. So you can have a story, right? And out of any story I give you, I'm gonna ask you, okay, what's the direction of the bias? So you have every time to think about it in terms of whatever I have explained, and this one is gonna be like the beta hat 2, and this is going to be like the lambda 1. Or this is how important, or the direction, or the correlation between the excluded variable or the omitted variable and the y, and the correlation between the excluded variable and the omitted variable. Okay, so let me give you this example for you to think about for next week. I want you to think about this model. So I'm not going to give you the direction of the bias. I just want to give you a story and you think about it. Suppose the correct form of the model is like this. I'm trying to test how crimes are affected by education and consumption of drugs, okay, plus a certain error term. And I'm gonna call this the correct form of the model. Now, suppose that I decided to, and this is I, right? So I have a group of people that I'm, it's not a group of people, it's a group of districts, okay? So I have districts. So district 1 all the way to district number 30, for example, okay? And now suppose that you decided to estimate this model, which is beta hat naught plus beta hat 1 education, I, and this is the wrong form. Why wrong form? Because I omitted drugs from the model. Wrong form. I want you to tell me what is the direction of the bias and why. You need to explain. Any question that you have and on any assessment, whether this is a quiz, assignment, or exam, when I ask you any question, just give me more details, okay? Because if you say direction positive, this is not a full answer. So I want you to think about what's the direction of the bias and why. And when I say the bias, remember, I'm talking about this. Why this one cannot be equal to this one. So why the expectation of beta hat 1 is not the same as the truth, beta 1. I do have certain bias. Is it more upward bias? Is it downward bias? Is it equal 0 bias? Okay, so you just need to tell me. Any question about that? There is no like a test as we did for the heteroscedasticity and multicollinearity, on which we can say that I have a test to determine whether I have an omitted variable bias. It all depends on how you study your model, okay? Okay. Okay, Dan is saying that he couldn't answer the practice question. How about you, Osman? Were you able to get the result of the VIF?
No, I wasn't able to get it. I couldn't find the file to even download in the first place, so I can plug it into that. And then I lost
file, which is the CPS 12, you mean?
Yeah, I couldn't find that under the Sakai when I was under the virtual lab. And then when I went to come back to here, like to continue our lecture, everything got closed out again. So I didn't bother even opening it again. I'm not going to lie to you.
Okay. All right. So the data set for the CPS 12 was already sent to you by email last week during our class. So maybe you can find it in your email.
No, I found it, but it wasn't able to download is what I'm saying.
Okay.
I have the line, the code line. I just don't know what variable for it.
What do you think, Dan? I can't hear you.
So I have the file. I can access to the file now. I just don't know what
the commands.
I have the regress command, right? I don't know.
Exactly. So once you get your regress command, all what you need to do is a VIF. You just type a VIF under it. So let me show you. I have it somewhere here. It's right before our discussion. Somewhere here. Okay, so yeah, so just need to type regress. Okay, so regress whatever the variables you have, AHE, age, bachelor, and female. And once you're done with the regress command, you just type the line right after it, VIF. That's it, variance inflation factor. You will get the table.
So age, bachelor, and female.
Yes.
And
Which is the
VIF at the end.
The variance, not the end, like the line right after it.
Like VIF.
Which is the variance inflation factor. Done?
It said is it like you type bachelor and then female and then you enter and then go down again, or just in one line?
Just one line. So you basically, okay, see here. So it's like this. Okay. So you have your do file, you type regress, okay, REG, AHE, age, bachelor, female. Done, right? So whether you have it on your do file, you highlight it and execute it. Number 2, VIF. That's it. Enter. You got the results.
Oh,
Okay, let me just go over the last 3 specification errors, and then until Dan is done. So these are not going to take, we're not going to take time in explaining these, because anyways, I'm going to go over them in the coming weeks. So we said we have the misspecification errors. We do have the omitted variables. We do have other 3. So let's talk about the next one. What if I adopted the wrong functional form? So number B, wrong functional. What is a wrong functional form? So a wrong functional form can be like any form of a model that I use. So suppose that your model is supposed to be anything, okay? yi is equal to beta naught plus beta 1 xi plus beta 2 xi squared plus beta 3 xi cubed plus ui. Suppose this is the correct form of the model. But, and I'm gonna say, okay, correct. But for some reason, you decided to regress a log model, natural log model of yi into the same set of regressors.
I think I got it.
Okay, I'll ask you in a few minutes, okay? I'm just finished that. Okay, so log yi beta naught beta 1 xi beta 2 xi squared plus beta 3 xiq plus ui. Suppose that this is the wrong model, okay? So your model is supposed to be linear in y, where you had y, but you decided to have, and this is wrong, okay? Wrong form. And you decided to have in log. So of course, every coefficient that you get would be biased. It's biased because you have implemented the wrong functional form. Okay, so what's the solution of this problem? Again, I'm not going to spend time here because this is actually our topic on nonlinearity, which we're going to spend like 3 hours on it. It's supposed to be 3 hours. Okay, so if your model is linear, you need to perform a test and check. Model linear, we used just a linear model, okay? Then just a regular OLS linear model. If the model is nonlinear, then I have to determine, is it a log? Is it log linear? Is it log model, right? Is it polynomial? I have so many options of nonlinearity. That's why you can run into so many problems about the wrong functional form. And that's why we have to study what are the possible types of models and how can I know which model best fit my data set. So if it is log, then we're going to, if it is linear, we already covered that. If it is log, then this is going to be the topic, our next topic, okay? Is it a dummy dependent variable? Is y supposed to be a dummy variable? Then this is our topic 7, okay? So we have different versions of the model, but for now, I'm just letting you know that you might run into a problem of choosing the wrong functional form of your model. How can I determine which model is the best? Is based on certain tests that we're gonna learn in the coming weeks. The other problem, which is C, errors in variables. So the errors in variables can happen because of, you can download the data set and something happens, right? You get incomplete coverage, right, of the data set. You might have wrong approximation, right? You might have wrong calculation. Let's say you're computing the inflation out of the consumer price index and you did a mistake in your computation, right? All of these possible mistakes can lead again to a bias, and this bias is not coming from you forgot a variable, but it's coming from your errors in your model. And to avoid this, you have, of course, to double check all your variables, right? Making sure that you're not doing any mistake related to the variables that you're downloading, you're getting the coverage that you need. Any approximation is done correctly. Any calculations are done correctly. So you basically want to avoid any possible bias coming from the wrong computation, okay? The last one, which is like the D, which is the simultaneous causality. Okay. Simultaneous causality. I know that all my regressions, I do have beta naught plus beta 1 x plus ui. All the time I'm thinking about, okay, x affects y, right? But simultaneous causality allows for the possibility that actually it might be the case also that y affects x, okay? So if y affects x, then I can have in my mind something like a reverse causality link, which is xi is also related to yi with a certain error term. So if I do have any changes in ui, which is here, any shock, like bad weather, right, it would affect my agricultural production. So if I have bad weather, a negative shock, it decreases y. If y decreases, then x, if this is positive, then x also is gonna decrease. Or I can say any change in y in the error term would be a shock to the y regression, would change yi, which in turn would change xi. Then this coefficient will be wrongly estimated because it will not only reflect the impact of x on y as I actually wanted, it would have a simultaneous causality, like the impact of both, right? X on y and y on x. So that's why if this happens, the solution would be use instrumental mental variable regression, which would be our topic on week 7. Okay, so which is the IV regression. The IV regression is used to overcome some of these issues. Okay, so I'm gonna stop here, and Dan, can you share with us your screen for the VIF test? Dan is gone. Okay, we're done with this topic. And as I said at the beginning of the lecture, I know that Lewis wasn't here.
Hello.
Hi, Dan, are you back?
Yes.
Okay, so can you share with us your screen? If I stop sharing, then you will be able to share, right?
Share screen.
I stop.
Do you see my screen? Oh.
Yes, you're supposed to click on the green.
Okay.
Perfect,
Yeah.
yes. All right, so what you did is, can you show me the regress command? Yes, that's perfect. Okay. Yes, age, bachelor, female, exactly that, like that. So what we did is a regression that has age, bachelor, and female. And then right after that, you type VIF as you did, and then this would give us the variance inflation factor table, which is exactly this one. And all what we need to do is, we see two columns here. We see the VIF and 1 over VIF. VIF is the variance inflation factor, which we have a benchmark for it. We hope that we don't get 10, right? We don't want number 10. And the next column, which is 1 over VIF, is the tolerance test, which we hope that we don't get a number which is less than 0.1. What do you get? Can you just take the screen up? So based on the VIF, what you can see, what can you say?
It's under 1. The VIF.
It's under 10, you mean?
Yeah.
So we don't have any problem, right?
Yes.
Exactly. So these types of questions would be like, okay, estimate this model, and once you finish estimating, I would ask you, compute the VIF. And when you compute the VIF, all what you need to do is to analyze what you see. If the number is less than 1, then that's perfect result, because you're not, yes, if the number is less or is less than 10, strictly less than 10, then you don't have any multicollinearity problem. Okay?
Okay.
So what we can say, we don't have any issues here. Okay, can you stop sharing, and I'm going to share with you my screen.
Okay.
So, okay, so what I want to share with you is my desktop. Can you guys see my do file?
Yes.
Great. So what I have here is similar to what we have seen on Dan's do file, but it's actually when I do it manually. So this one, I'm not going to like ask you to memorize it or anything, but let's check the multicollinearity part. So as I said, if you just type VIF, you will be able to get the table. What if I want to do it manually, right? So if I want to do it manually, I already gave you the equation. It's 1 over 1 minus the r square of a regression that starts with one of the x's. So let's say if I have this model, this is my main model. I'm trying to find out whether education is affected by a certain test and a group of other factors, including tuition, distance to college, and so on. And I might be interested in finding out whether I do have a multicollinearity between the x's. Remember, multicollinearity is all about the x's, not about the y, it's not about education. So I can either type a VIF command as Dan did, or I can do it manually, okay? So let's see. So I already have the data set right here, which is the college distance data set. And what if I wanna do, okay, this one is exactly like what Dan did. So regress of y on the x's, and I'm doing a VIF. And what I'm getting is the VIF of each x. And again, good result because this number is less than 10, which is basically saying that I don't have any multicollinearity issue. So let's see if I'm trying to do it manually by test, which is one of the x's. Can I get this 1.04? Can I get this 0.96? So how can I do that? So it's basically if I do the regress of by test on all the x's, and I can compute the VIF by taking the r square of this regression, right? Of this whole regression, not just the highlighted part, of this regression. And I'm computing it 1 over 1 minus the r square. The E here is the vector that compiles all the r squares of the model, and it has it in there. Or the tolerance test, which is the inverse. So what we do here is, of course, you don't have to type quietly. Quietly means that I actually don't want to see the output of the regression. I don't care about the output now. I don't want to see it now. So I'm just telling Stata don't compute it. So what you do that, when you do that, so basically you're getting the same numbers, right? So I did the regress. As you can see the regress, I don't see the output because I wrote quietly. So the by test is 1.04, and this is what I was getting here. And then the tolerance test is the same here. So you can either do it manually or using the VIF command. Any question? Okay, guys. So let me go back to the iPad. And in the iPad, I'm going to start the topic on nonlinearity, which is actually supposed to be our today's topic, but I'm working with certain lag, okay? As you can see, like these topics usually in class, I take like 3 lectures to cover each topic, and now I'm supposed to cover each topic in like about 3 hours, which is like very short amount of time. So anyways, I'll try to cover some of the part of today's topic, which is nonlinearity. And then I'm going to complement that with a couple of videos, a couple of recorded videos. So today's topic is nonlinear models. So the nonlinear models, we have actually 3 types of nonlinearity. So we have polynomial models, like quadratic, cubic, the power 4, whatever. We have log models or logarithmic models. And we have interaction type model. And we have a combination of the 3. After we're done, we're going to go make our life complicated, and we're going to kind of blend these models together and see we can get different specifications. So let's start with polynomial models. because it's my favorite one, and it's relatively the less complicated one for students to understand. So what is polynomial models? Polynomial models is a model that allows for some powers to the x. So it's like this: beta naught plus beta 1 x1, or it's actually the same x, xi plus beta 2 xi squared plus beta 3 xi cubed, and keep going, beta plus beta k x k to the power r, right, plus ui. If this r is equal to 2, then this is a quadratic model. If it is 3, then it's a cubic model. If it's 4, then we start saying to the power 4, and so on. 5 to the power 5, and so on. Usually in economics, we work most of the time with quadratic models and sometimes with cubic models. I would say this is like more commonly used type of model. We don't usually go to the power 4 and power 5 and so on. So what's the idea of nonlinearity? So if I have a model like here, age and income. Since we started this course, we were all the time assuming that this relationship is like straight line, right? I have observations between people I have, and these observations can be grouped into a certain line where as the person gets older, the person gets higher and higher and higher income. Okay. However, in nonlinear models, we basically try to make it more realistic and say that it's not like the increases are not constant over time. The slope is not constant over time. So here we said that the change in income, because of the change in age, is constant, right? When I talk about linear. However, it might be the case that, or more realistic is the case that the increases are high when the person is young. As you get to a certain age, the number gets smaller and smaller and smaller and smaller until you get like up to a flat curve. So the increments or the increases increase, but at a decreasing rate. And this actually more realistic type of model, because you will not get the same additions to your income exactly the same when you were 30 as the same as when you're 40, as the same as you're 50, and the same as you're retired. Okay, so the changes might be big at young age, gets smaller as the person gets older, right? So this gap is supposed to be bigger. Of course, my hand drawing is not as accurate as supposed to be, but at young age, when you're like 20 to 21, is not the same as from 50 to 51. Of course, and again, holding all other factors constant. The increases might be, let's say, $5 from 2021. It might be like $4 from 51 to, or from 50 to 51, for example. So nonlinearity is also related to any other models, right? So when I say price and demand, when you always like have it as a linear, is it always linear? No, it might be actually non-linear. So it might have some curvature, right? So this curvature, if I have a relationship between X and Y, right? And again, suppose that this relationship is like that, supposed to be like some curvature, and I'm fitting a linear line, then this linear line might not get all the points that are here at the curvature part. So I might need to add some bends to the line. I need to bend this line a little bit. So I need to bend it, like bend like this, bend like this, bend like this. So how many bends I need to add? If I have R equal to 2, then I'm bending it twice. If R equal to 3, then I'm bending it 3 times. So the more bends I have in the model to in the regression line or the estimated regression line to fit my data set means that I'm adding more and more x's in the model. So I want you to imagine that adding more and more x's in the model has a positive and negative effect. So if I move from a model that is like yi equal beta naught plus beta 1 x I, right, plus ui, and I added one bend to the model, beta naught plus beta 1 xi plus beta 2 xi square plus ui, and I further add more and more bends, beta naught plus beta 1 xi plus beta 2 xi square plus beta 3 xi cube plus ui. The more I add quadratic and cubic terms, it's good because I might be able to fit all the observations and the dots I have in the scatter plot. But every time I'm adding a new or additional coefficient, I'm losing degrees of freedom, right? Remember, n minus k minus 1, the higher the k, the less is the sample, like the total sample size after adjusting for degrees of freedom. So adding r, let me write it here, as r increases or as you add more and more bends to the line, it increases the bends, right, in the line to match all the points of the true population. So, which is good because it matches the population like scatter plot. However, it's bad. So this is a positive effect and this is a negative effect because losing degrees of freedom. So I have to make, this is freedom, okay? Because as the k increases, n minus k minus 1 decreases. So the adjustment of degrees of freedom makes the sample size get smaller and smaller and smaller. So I have to make sure that I follow a certain test that would help me to determine how many bends I need in the regression line, or whether I don't need at all, like whether I prefer to have a linear model instead. So there are two ways. So how to determine the number of polynomial terms in your model. So there are actually two ways, and make sure that it's not like you decided on your own, okay, I think I need to add only 2 r equal 2, which is quadratic, or it's not like, okay, I need to have 3. You have to follow certain tests, and you have to make sure that this is actually what you need, because the more r's in the model, the more polynomial terms in the model, it might be good and it might also be bad. So you have to do like an educated test on your model. The first one is called the sequential hypothesis test, and the other one is called the block test. So you can do a sequential or a block or a combination of the two. How it works. So let's start with the sequential hypothesis test. So remember, what you need to do is you need to determine whether I need up to 4, up to 3, up to 2, just linear. So you start with the sequential hypothesis test. So you first of all, you start with pick a maximum R. So you say, okay, I think I'm going to choose R equal to 3. And this is just, you start by a certain guess. In econometrics, we start with 4, okay? So this is commonly used. So let's say r equal to 4. So your model is going to be equal to yi is equal to beta naught plus beta 1 xi plus beta 2 xi squared plus beta 3 xi cubed plus beta 4 xi power 4 plus ui. This is ui. Okay, so you start with a certain number of powers, and we said, let's say 4, because usually this is what we're going to start with. And you estimate your model. So you go ahead and you estimate your model and you check. So you pick an R and then you estimate the model. Okay, let's say you estimate the model in this data, and after you estimate the model, all what you need to do is check the very last coefficient, beta hat 4. If beta hat 4 is significant, then you're done, and you're going to say model is power 4. That's it, and you're done. If insignificant, you go to step 2. So in step 2, you estimate a smaller model, yi equal beta naught plus beta 1 x1i plus beta 2 x2i plus beta 3 x3. What is this? I'm sorry. It's not 3i. And you guys, you don't tell me that I'm doing any mistake. Okay, let me make sure xi. Okay, I just wanted to make sure I'm not doing the same mistake here. So this is x. It's only one x, okay? So xi squared xi cubed plus ui. So you estimate a smaller model in which r is equal to 3, okay? And then check beta hat 3. Again, follow the same methodology. If significant, the model is power 3. If insignificant, go to step 3. So if significant, you're done. Then you're done. And your conclusion is the model is cubic. If insignificant, go to step 3. In step 3, you estimate a model in which r is equal to, or you estimate yi beta naught plus beta 1 xi plus beta 2 xi squared plus ui, okay? And again, I'm sure that you guys can expect what we're gonna do next. What do you think? Someone's gonna tell me. In step 3, what you need to do?
Check the significance level
Of
beta 2.
exactly. So check beta hat 2 significance level. If significant, then you're done. And your model is quadratic. And if not, you're actually done too. Your model is linear. That's it. Okay, so as you can see, it's called the sequential hypothesis test because it goes in sequence test, right? I'm doing this hypothesis test in sequence. I start big, right? I start big to small. Actually, some people, they would start from small to big, but I prefer to go from big to small. And the approach that you have in your textbook is the same, big to small. And you start big, usually we start with R4, you keep eliminating, right? If the last power or the last coefficient of the last power is insignificant, eliminate, get a smaller model, check If the significance of the very last coefficient insignificant, eliminate until you try to find out the actual number of polynomial terms that are needed for your model. So as I said, you have two options, right? Sequential or a block test. If you're doing an exam and I'm not telling you which test to use, then it's optional. But usually in real life, I would do that both. Okay, so what is a block test? A block test would be like just taking a block. I have this model here, right? And my question would be, is your model to the power 4 or linear? So it would be like this. Let me have a clean slide. So in the block test, block test is simply an f-test. As you know, f-test is used when I'm testing more than one coefficient at once. So if I start with this model, yi beta naught plus beta 1 x I plus beta 2 x I squared plus ui. The question would be, is the model of degree 4 or linear? Okay, I can have also another question. Is the model 3 or linear? Or is the model 4 or quadratic? So if the model, let me start with this one, is the model of degree 4 or linear? So if it is up to here, it's linear. If it is up to here, then it's to the power 4. So I actually need to check the statistical significance of the additional part. So I will need to perform an f-test in which I'm testing whether the expectation of the additional terms, beta 2, is equal to the expectation of beta 3, is equal to the expectation of beta 4, is equal to 0. And the alternative is one of the above restrictions does not hold. Okay, so here, suppose that I get f that I calculate, okay, calculated, equal to any number. I'm just gonna make any number, okay, 17. Suppose I get the f of this test equal to 17. I need to compare this with the table. And I have to decide which significance level I need. Suppose that I'm just making an assumption, I used 5% significance level. I need to check f 3 restrictions, 1, 2, 3, so 3, infinity. And this is going to be my critical value. Okay, so f3 infinity, so I'm not sure where I can find the f table. This is the chi-square table. Let me see. No, this is the, I have it somewhere. It's right here. Okay, this is the F table. And I have, actually we used it before. Okay, so we used 3 before. So I have 3 restrictions, right? And infinity, so 2.6. So my critical value is definitely smaller than, right? So this is 2.6. So my table would be, I mean, like my graph would be, or my distribution would be like this. critical value of F3 infinity is 2.6. The number calculated, and when you ask me where did you get the 17 from, I just made any number, okay? So the 17 would be here. So the F calculated exceeds the F critical value, which is 2.6 and 17. So we are at the rejection region. So our conclusion would be, so that means we are at the rejection region. So reject the null. And the model is, I'm rejecting this. I'm rejecting that they are equal to 0. So what is your conclusion? Your model is linear or nonlinear? Anyone? Lewis? Okay, Lewis is not here. What about Osman?
No, I'm just not really too sure on the answer.
So here is the, so this is the critical value of 2.6, right? And we get a 17, which is the F calculated. So you are rejecting the null. The null is saying that these coefficients are equal to 0. So you are rejecting this. You're accepting the alternative that they are supposed to be there, right? So what do you think? Is the model linear or nonlinear?
Would it be non-linear because you are rejecting the null?
Exactly, that's correct. So since you are rejecting the null, then you're saying, I'm rejecting that these are equal to 0. These coefficients need to be here because at least one of them is not equal to 0. So you have to keep them, and you're basically going to conclude model is nonlinear, or be more specific, is nonlinear of degree 4. Okay? Is it clear?
Yeah.
By the way, Othman, I'm drinking Moroccan tea. You're from Moroccan, right? From Morocco?
Yes. Do you actually want to know something?
This is the mint from Morocco.
Yes, I'm actually, as we speak right now, I'm heating up a cup for myself.
Okay.
My
Okay.
mom mints outside.
Oh, okay. Yeah, I love the Moroccan tea.
Yeah, it's
So, yeah. Okay. And in Egypt, I'm Egyptian, so in Egypt, as you know, like we have also mint, but for some reason, the one I got here in New York is from Morocco. So I found that it's more tastier than the one we have in Egypt.
I feel like the only difference sometimes is that, like, when it comes to like Moroccan tea, at least like when my mom makes it, she just packs it a lot with sugar. So it'll make it like really tasty as compared to like when I just drink it like sugar free.
Yes. Thank God I started to stop sugar. It's just a nightmare having like a lot of sugar. But you're right. Actually, the mint without sugar, it's not the same. It's totally different. Yeah.
Yeah. That's how I've been drinking it lately too, because of like dieting purposes too. I cut out sugar.
Yes. Since Corona thing, we're staying home, no exercise. I decided, okay, no more sugar.
Yeah.
Okay, guys. So what we did is a block test. As you can see, the block test is just take things as a block. I did just 4 versus linear. What if I do it like 3 versus linear? Then you're going to do the test on just the square and the cubic term, you know, and then you perform the F test, and it's gonna go the same way. Okay, so let me focus on the quadratic model. Why I'm focusing on the quadratic model? Because this is what we use a lot in most of our applications. So I'm going to give you like 3 important things to talk about. So in quadratic models, or R equal to 2. Our model beta naught plus beta 1 xi plus beta 2 xi squared plus ui. Here I have only one variable xi. Let's say this is income squared, okay? Or this is age squared. Of course, I can add other factors to the model, but let's just focus on one variable, okay? Just one x. So when I talk about just one x in the model, I just want to focus on important things. We want to talk about a turnaround point, okay? I want to talk about the slope, actually before the turnaround point. What's the slope of this relationship? What's the turnaround point? And I want to talk about the exact versus approximate effect. So those are very important points when it comes to a quadratic model. So the slope. The slope is something easy to remember because you've done it multiple times in your previous math courses. So slope is the change in y because of the change in x, or you can think of it, you get the derivative of this equation with respect to x. Okay, so if I get the derivative of this equation with respect to x, right, it's going to be, okay, I have this one, the derivative of this equation with respect to x, I'm left with beta 1, and the derivative of this part with respect to x is going to be like 2 beta xi, right? And this is going to be the slope of this function. Previously, in all the models that we discussed since the beginning of the semester, our slope ends here. It was just this part. Now our slope, we have an additional part, or that could be positive, that could be negative. It depends on the relationship. Let's say here, like if I have it exactly as you see it here, then it's going to be like the effect of x is positive and it's increasing, or it's increasing at an increasing rate, right? So always the second part is about the rate and the first part is about the direction of the relationship. So I can rewrite this into this way. The change in y is equal to beta 1 plus 2 beta, this is actually beta 2, right? 2 beta 2 xi times the change in xi, right? Let's add the I everywhere. Does anyone have any question about that? This is just rewriting. If this is 1, I'm rewriting 1 and I'm getting this equation. So if I'm giving you some numbers, okay, if I'm giving you the change in the age of a person by 1 year, and the person is already 20, and suppose I'm giving you the coefficient of beta 2 and beta 1, then you can easily compute the change in income, okay? And I'm going to show you with examples. When I use it this way, or when I use this equation, I say this is called approximate effect, right? What is the change in y for a small change in x? Whenever I'm using this formula for 1, which is actually computed from the first derivative, then this is all about the small changes that happens in x. It could be by 1 unit. Let's say as the person gets older by 1 unit or 1 year, right? Or as I increase the distance by 1 mile, so it's always 1, you know, it's just 1 unit. Another thing I want to tell you is, again, I'm sure that you know that. So if I have this relationship, and this is age, again, I'm just using the same, and this is income. And as the person gets older, let's assume your income increases, reaches a certain maximum, and starts to stop or decrease. So this is called the maximum. This maximum, the slope here is equal to 0. So the slope stops moving at the maximum or the minimum point, right? Slope is 0. So if I can get this slope is equal to 0, then I can get this turnaround point. We call it a turnaround point because it turns around from being positive to negative. Okay, it could be maximum, it could be also minimum, right? So if I'm talking about a cost relation, so this is the cost, let's say this is the units produced, and this is the total cost of a certain firm. As you increase your production, your cost decreases, reaches a certain minimum, and then you start to increase, and this is the total cost function that you have taken in micro. At this point, again, the slope is, this is a minimum point, and at the minimum point, the slope is again stops moving and it's equal to 0. So we might be very interested in knowing what's the turnaround point, at which age exactly I will reach my maximum income, or at which unit produced, if you're the producer, I can reach my minimum cost. Okay, and if you remember, like this one you have taken in micro, and you talk about economies of scale, and if you reach you keep decreasing cost because of reaching economies of scale, and then constant return to scale when it reaches the 0 point. So saying that, then I might be interested at the point at which my slope is equal to 0, because at this point I call it the turn around point, or the point at which I reach the maximum or the minimum, depending on the relationship I have. Okay, so the slope, I know from the previous slide, slope, which is the change in y due to the change in x, was equal to, go back here, where is it? It's right here, right? I'm going to set this equal to 0. So, which is equal to beta 1 plus 2 beta 2 xi, set this equal to 0, and solve for x, and then you set equal 0, then you're going to get beta 1 plus 2 beta 2 xi is equal to 0. That xi is simply equal to beta 1 over 2 beta 2. Just have your absolute terms because we don't want to be in the negative side of the x, right? So if beta 1 is positive and beta 2 is negative, then I say this relationship is increasing at a decreasing rate, like here, increasing at a decreasing rate, okay? And I have a an inverted U-shape relationship, and I can have a maximum. Okay, so, and of course I can flip everything and say the opposite. So this means that the relationship has a maximum. Okay, it increases at a decreasing rate, then I can reach a certain maximum. And of course I can say the opposite, and this is if, and this is one, let's say this is graph 1, so this is like graph 1, and I can also say if the opposite beta 1 is negative but beta 2 is positive, then I have my relationship is decreasing at an increasing rate. It has a minimum, right? And this is like graph 2. Okay, this one has inverted U shape. This one has a U shape. Okay, so I might be all the time interested in this turnaround point or cut-off point. You can call it cut-off point or a turnaround point. And you see me like mentioning both every time. All right, so let me make sure that what we did cover so far. So I said that, where is it? Yes, we talked about the slope, the turnaround point, the there is an end here, okay? There is a exact and approximate. We actually mentioned the approximate effect, which is actually this one, okay? What is the approximate effect of X on Y? And whenever I'm using the slope function to solve for Y, then I'm getting the approximate effect, because it reflects the changes in Y because of small changes in X. What about the exact effect? Exact effect, actually, it's easier. It's just plugging in into the function the numbers. So let me show you. So what is exact effect? Let me give you this example. Suppose I have an equation in which I'm trying to find out the relationship between the wage of the person, experience of the person, and I'm sure the effect of experience on wage increases at a decreasing rate. So here we have a negative. And I'm asking a group of people, suppose the group of people I'm asking, what is your age and what, sorry, not age, wage. Okay, wage and experience, suppose I have like 100 people. So I have this equation repeated 100 times. Now, suppose I estimated this in theta and I got these coefficients. Wage hat is equal to 3.73 plus 0.298 experience minus 0.0061 experience square. And again, this is based on actual data set. I'm asking you to compute what is the exact change in wages for the change in experience from 0, you have 0 experience, to 1 year of experience. What's the effect on your wages if you move from 0 experience to 1 year of experience? So what you need to do is very simple. You need to plug in 0 here one time, get wage, and then you're going to repeat the same for 1 and get the age. I keep saying age, it's wage. And then get the wage for 1 year of experience, and then get the subtraction or the difference between the two. So I'm going to do this one, and I'm going to ask you to do another one. So at experience equal 0, then if I plug in 0 here, 0 here, I'm left with this one. Wage is equal to $3.73 per hour. Okay, so this is per hour. At experience 1 year, then wage is equal to 3.73, but I'm going to add to it experience 1 minus this amount falls by 0.0061 squared, which is just 1. Okay, and then the number that you will get is 40219. And this is telling me that a person with 1 year of experience, the amount of wage is $4.0219. Remember, the question is about the change, not the absolute number. So you will need to get the difference between, let me call this one as equation 1, and this is equation 2. So I need to do 2 minus 1, and this is it's going to give me the change in wage is equal to 4.0219 minus 3.73, which is equal to the difference 0.2912. So there is actually only a few cents difference between moving from no experience to just 1 year of experience. The person's wage is going to increase by 29 cents per hour. Any question?
All good.
Perfect. I want you to, your homework is, and I'm going to ask you this next week, your homework. I want you to redo the above for experience, or the increase in experience from 2 to 3 years, and from 0 to 7 years. I want you to give me 2 numbers next week, and I'm going to ask you, I'm going to call your names and just ask you what's the number you got, so that instead of me just keep on typing equations and numbers, I think it's straightforward. So you just need to plug in these numbers, 1 time for 2, 1 time for 3, get the difference. 1 time for 0, 1 time for 7, and get the difference. And then the intuition behind that, I'm going to talk about it next week. This is, we call, and remember, this is called exact changes, because exact changes, I'm just plugging in the numbers into my equation, getting the exact changes in wage. What about approximate? Approximate, I already mentioned it. I said you just need to use this equation, right? You just need to use this equation. What is this equation telling us? If I'm asking you from 0 to 1, the change, which is right here, is simply equal to 1 minus 0 is 1. This is the original level, which is 0. So you need to plug in 0 here and 1 here and get the number. So let me do it here. So I'm going to repeat this question for the approximate. Okay, so let's repeat. Changes in experience and compute the approximate effect. On wages. So I want you to remember that I already gave you the equation, right? So I already told you that, and this is given in the previous slide, that wage hat is equal to 3.3, no, 7, this is 7, 3 plus 0.298 experience minus 0.0061 experience squared, right? Now I want to get what is the first derivative of this function with respect to experience, and you do it as you do in math. So the constant, just ignore it, and 0.298 minus 2 times 0.0061 experience, right? And if my interest is about the change in wage, then the change in wage is equal to times the change in experience. You can actually write it in terms of deltas, but I write it in terms of the differentiation sign because I just want to make sure that you understand these are small changes. So you can write it this way. The change in wage is 0.298 minus 2. Okay, so again, the same question. What is the impact of the increase in experience from 0 to 1 year? All what you need to do is, here the change is going to be 1 and the original experience is 0. So the change in wage, which is we call the approximate change in wage, is 0.298 multiplied times the original experience is 0. Everything is multiplied times the change in wage. 0 minus 1 is 1. Then the number that you will get is simply the intercept. So the approximate change in experience, the approximate change in experience because of the increase, the approximate change in wage because of the change in experience by 1 year is about 29, is about 30 cents, right? Which is same as the answer we got. We're very close to the answer we got here. So you might have a question that is asking you to compute exact or approximate, okay? The exact, you just plug in numbers and you get the difference between two equations. However, when it's about approximate, then you basically need to use this equation, or I mean this equation, you plug in the numbers that I'm asking you to do. So again, I want you to redo the above for the increase in experience from, it's the same thing, okay? What did I ask you? Wait. 2 to 3 and 0 to 7. Okay, I'm just gonna do the same. Okay, 2 to 3 and 0 to 7. And then we're going to compare our answers next time and see, okay, when I'm going to, when should I use the approximate and when should I use the exact? Okay. Any questions? On your textbook, you have actually nice examples in which you have income and income squared. Okay. I want you to check that because it's related to what I'm discussing, but actually what you have in your textbook is more about exact changes. Okay, it's not about the approximate. Make sure that you complement your notes with your textbook, because personally I like the approximate changes. It's much easier and it would give me almost the same answer. So here I have my answer is 0.298. Here my answer is 0.2912. If you tell me approximately 29 cents versus 30 cents, I say the answer is the same. Okay, so what else? Let's see the turnaround point. So I told you here that, okay, I might also be, where is it? I'm sorry. Okay, the turnaround point. I'm giving you the wage and experience example. And I might be asking you, okay, what is the turnaround point of experience? Like, yes, the relationship is positive. As you accumulate more years of experience, your wage will increase. But what is the point at which experience would have no effect on wage? And what is the point at which, if I accumulate more experience, would decrease my wage? Okay, of course, it doesn't make any sense, right? If someone has like 10 years of experience and he adds 11 years of experience, I'm sure that the wage will not decrease, but it will not increase, right? It might fail to keep on increasing. It might have a negative point, but it might be insignificant. So let's use our model. Using the wage experience model, compute the turnaround point of experience. Okay, so turnaround point, if you can just look here, this is what you need to use. And this is actually based on solving for X. So all what I need to do is to get the beta 1 and 2 over beta 2 and then have absolute terms and just avoid any negative values because I'm not working with the negative side of the X. Okay, so your model is, remember, your model is we said the change in wage because of the change in experience was equal to 0.298 minus 2. I keep writing it so you're not lost. Experience. Okay, now set slope equal to 0, then and solve for experience. Now experience is equal to 0.298 over 0.0061. Get this in absolute term because this one actually had a negative sign right here, and this would give me 24.43 years. Remember, the unit of measurement is following what the question is asking you. So this one is telling me like this: this is wage, this is experience, the relationship is positive at a decreasing rate. So it's positive, yes, but this positive is decreasing, reaching a maximum, decreasing, right? I'm interested in the cutoff point. The cutoff point is at 24.43. Okay, so this means that if you reach this point, the slope would be, slope is 0, the slope would stop moving, and this is your cutoff point. Any point before the 24 years, 0.43 is a positive relationship, or a wage would increase. Any point after that, wage would fall. Someone would ask, okay, what do you mean? Like, if I accumulate 25 years of experience, I will be in this part and my wage would fall. The good answer would be, go ahead and check your sample. How many people are in this area? If I do have only 2 people or 2 persons in this area, then it might be insignificant, right? The result is insignificant. Mathematically, it says, yes, it would decrease, but it might be some number that is statistically insignificant, like probably 0.0001 cent, okay, which might be something like small number and insignificant number, but still there, it's still mathematically there, right? All right, everyone, so any question? Any question? Okay, so as I said, I want you to solve the 2 questions I told you to do. What we're gonna do next week is we're going to check this model on Stata, do everything that you see here on Stata, and instead of me showing it to you in the remaining 13 minutes, I'm going to give you an introduction to the log models. Okay, so in the next week I'm going to be giving you other, just want to start with something interesting because log models are not interesting. So let me try to find for you something interesting. In the meantime, do you have any question, guys? Okay. So we're actually done with the polynomial models, and our next topic is about log models. So what is log models? So log models, suppose you are interested in the percentage change. I'm not interested in the changes in wages per dollars or per cents. I'm interested in the percentage change. Or suppose that I'm comparing different professions. Let's say teachers versus truck drivers versus nurses versus doctors versus engineers. And I want to know what is the percentage drop in their wages because of the virus, let's say. In order to compare between different professions, it's more interesting to compare in terms of a percentage drop rather than dollars drop, okay, on average. So I can say a sentence like, on average, the wages of, or the salaries of engineers dropped by 3% compared to the wages or the salaries of teachers. I prefer to say it that way than saying the salaries of engineers dropped by $3,000 compared to the average salary of teachers. So in terms of comparison, it's much easier to use percentages because your unit of comparison is the 100, right? So it makes your comparison more interesting, easier to understand. Like when I tell you 3,000, okay, who cares? What's 3,000? 3,000 compared to what? What's the origin, right? Was it 3,000 as compared to, they used to get like 1,000K, or they used to get, I mean like 100K, or they used to get 50K? I don't know. So using a benchmark, which is our 100, which is the percentages, it's much easier to understand. So in log models, again, I might be interested in talking about percentages rather than dollars or miles or scores of a test. When I tell you your final decreased by 2 points, you might be more interested, okay, is 2 points, is my exam out of 20, is my exam out of 100? So when I say your exam dropped by 2%, then you understand, okay, it's 2 out of the 100, then I can use it even to compare it versus 20 points, if the exam was out of 20 points. So in log models, we have 3 types. I have a linear log model. I have log linear model, or log model. So linear log is the y is linear, x is percent. Here, the y is in percent, x linear. Here, both y and x are in percent. So a linear log would, let's start with the linear log. So a linear log model would be like this. Y is linear, beta naught plus beta 1 log x plus ui. So x is in percentages, y is, let's say, any unit. Could be dollars, could be miles, could be cents, anything but not percent. So this model would be, what is the effect of a 1% increase in x on the, let's say, dollars change, or the dollars changes in y. Of course, I don't have to say dollar changes. I can say on the changes of y, but I just want to make sure that you understand is that y is another unit of measurement, but not percent. So in this type of models, I would be interested in the fact that x is in percentages, y is in dollars. Like, what is the effect of a percentage change, of a 1% increase in experience on the dollar change in my wage? I can also have y log, so log linear model would be like, okay, y beta naught plus beta 1 x plus ui. Here, what is the effect of a 1 year increase in experience on the percentage change in wage? This is an example on this type of model. So here I'm taking y linear, and it's in years, could be in miles, could be tenths, anything on the percentage. So this one has to be in percent. And finally, I can have it like log. So this is a famous model, which is the elasticity model that you have in your micro. So here log y is equal to beta naught plus beta 1 log x plus ui. So the percentage change in x affects the percentage change in y. and I want you to refer here to elasticity model. So elasticity models, which is the price elasticity of demand, for example, it can be any other type of elasticity. We abbreviate it as PED, price elasticity of demand. It's all about the percentage change in my demand or quantity demanded of good X because of the percentage change in the price of X. This is an application that you got in your micro, price elasticity of demand. So the price elasticity of demand is a great example of a log-log model in which we are interested just in the percentage change, I'm not interested in how many units are sold or demanded versus how many dollars increase or decrease in price. I'm interested in percentage changes. Okay. So each and every model has like a detailed interpretation of the beta. So the beta attached to the X here has a different interpretation, whether I'm talking about linear log, linear, log, and it requires some, like you need to be really focused so that you're not doing any mistake in understanding it. So let me start with the first one. Just wanted to give you an example. So this is a good start. Okay. Suppose that, let me start with a linear log. We actually have 4 minutes left. Okay. So I'm gonna stop with the slide and then so suppose the linear log y is equal to beta naught plus beta 1 log x plus the error term. Now let's change x. Anytime I change this, it's reflected here, right? So the change in y is equal to beta 1 the log of x plus the change minus the log of x without the change, right? So what is this? This is the new x, x plus the change, and this is the old x. This is the new x, okay? So this part can always be approximated as, like, I can remove this whole thing, which is like looks complicated. I can say it's approximately equal to the change of x over x. And I'm going to prove that next week. So I can rewrite this by saying, okay, it's equal to beta 1 times the change of x over x. In other words, this is the fraction, right? So this could be like 1 over 100, which is 0.1, okay? So that means beta 1 is equal to the change in y because of the percentage change in x, okay? So y here reflects the unit change in y because of the percentage change in x, all right? I'm going to leave you with this slide, and I'm going to talk about the log models next week in details. And we're going to do this data application of the polynomial models. I didn't want to do the polynomial application today until you guys digest the information. Remember to do the homework that I asked you to do for the change in experience, right? For the approximate and the exact changes. So next week when we start, make sure you come on time, because I see some students, they come like 15, 20 minutes late. If you decide to attend the class, please come on time. I want you to come prepared. I want you to come with this data open in your background, so that when we have an application as we did today, like we don't have to wait. If you have any technical issue, like a couple of you have sent me emails, or like today when Osman said, just make sure that you contact the help desk and try to find out how can you avoid these kind of technical issues while working virtually in your computer. Okay, so come prepared next week with your data open, solving these questions. I'll call your names, come on time. I see only 2 students who come on time out of a class of 5 students, okay? All right, I'll see you next week. If you have any question, you can ask me on the discussion forum. All right, students, I'll see you next week.
See you next week, Professor.
Thank you. Bye.